So this is gonna be about measuring FNL in a kind of new way, and let's work with these people that are involved to various degrees in that. But I think it fits into this meeting because it is about measuring this parameter. So roughly speaking, of course, you know the CMB modes are running out. There's a limited number of them, and then there are galaxy surveys, but of course they have this nonlinearity problem. So something one can hope to do is that for certain parameters, for certain non-Gaussianities, one can find other ways to constrain non-Gaussianities than just by increasing the number of modes. And in this talk, you will use KSC, the KSC effect to measure the velocity field, and then use that for sample variance cancellation for the experts to get this FNL parameter. I'll explain in a minute for those who don't know that what it is. Okay, and so why we're doing this now, basically why it's the right time to work on this is because now you know these upcoming CMB experiments are probing the high L range of the CMB, and at high L, when you clean out the frequency dependent stuff, then you're dominated by the KSC effect. So you know here kicks lensing in, and then there's the KSC effect. And the KSC effect is simply the rescattering of photons on moving electrons in the intergalactic medium, and so on all moving electrons, and so it's proportional to in one direction. The KSC effect is proportional to the line of sight integral over the density of electrons times the radial velocity. So it's like this is kind of a Doppler shift of the photons. Okay, and what we do here, KSC tomography, is cross-correlating the CMB and large-scale structure. That gives some 3D information back. That's why it's called tomography. And in particular, so the probe that we are using here is a quadratic estimator, which is something that's very widely used in cosmology, right? So what we want to do is we want to measure the large-scale radial velocity field, VR, of all matter, and reconstruct that from the small-scale cross-correlation of the galaxy density and the CMB. So this is a 2D probe here. This is the CMB. Here's kind of a flat sky approximation. That's why it's all in K instead of L. And this is the galaxy field. So we take a survey with a lot of galaxies. We take a CMB experiment with the CMB at high L. And then we cross-correlate these two, basically with a certain set of weights. And this gives us back an estimator of the velocity of the electron velocity, of the radial electron velocity. Okay. So this works similar to lensing. For those who know that a quadratic estimator in lensing uses two small-scale powers of the CMB temperature to reconstruct the large-scale lensing potential. Okay, so and why are we doing this in this case here? So interestingly, now when you set up this estimator, you can calculate, of course, what the noise level is of the estimator, and the noise for each mode is independent of KL. It depends on the galaxy density, it depends on the CMB properties, but it does not depend on the wavelength of the velocity field mode, which is basically because you just measure them right away, the velocities. So, and this has now a useful property that is useful for FNL, and the property is the following. Now, as you know, in large scales, which is where we measure this velocity field with the KSC, you can use linear perturbation theory, and you can relate the velocity field to the delta field, to the matter perturbations in a direct way. So this means that if we measure this here, then we get from the velocity field we can calculate what the matter perturbations are. And now, as I said before, the velocity field noise is constant in K, but if you use this relation, you will get a K-square dependence in the noise that comes from this reconstruction. And so this means that with this method, you can measure the radial matter perturbations on large scales with lower noise than the shot noise. So this is an example here for a real experiment that's upcoming. This is DESI, and here with some CMB experiments, for example, the CMB S4 that we've been hearing about from referral. And so if you're DESI gives you this shot noise here on these modes, and this here would be the noise that we get from the velocity reconstruction. So we get a better noise on large scales. So now, what can we do with this? And the thing that comes to mind immediately to a cosmologist probably is scale-dependent bias. Now, I guess most people here know what that is, but for the pure string theorists, so the idea is, right, that the matter power spectrum and the galaxy power spectrum on large scales is related by a parameter called the bias. So galaxy power is larger, so the bias is some order 1 quantity, but it's usually larger than 1 for larger halos. And often, for the halos we measure. And it has, if f and L is not 0, then there's this famous scale-dependent bias that was found by Neil Dalal and others. And so that kicks in on the largest scales. And this is the signal that we are after. And now the reason, but as I said before, with KSC tomography, we measure the overall matter, since we measure the velocities, which are given by the gravitational potential. So we measure the overall matter. So we measure this curve, which is not F and L dependent. So you would think it's useless for F and L. But there is a way in which it is useful, which is because the relation between these two parameters here, between these two modes here, is not stochastic. It's given by the bias. So basically, if you can measure once, this is a cartoon picture of what's going on. But basically, if you can measure once the biased galaxy mode, and once the unbiased matter mode, and both of these are of course stochastic quantities, so they come with cosmic variance, but if you take the ratio of the two, in principle you measure exactly the bias, or here on large scales, as I said, the total term here is this bias plus the F and L, this F and L dependent term that comes with a k-square factor. And this is called sample variance cancellation, and this idea was first explicitly, I think, proposed by Urs Seljac. However, not with this velocity field probe that I'm talking about today. Okay, so this is our plan. So now this is the setup, and now we put it all in equations. So what we are going to do, we measured the velocity field. We're actually measuring, as I said, only the radial velocity field with the KSC. And these are the galaxy modes. And so this is the data that we measure, and then we run the usual kind of Fisher forecast. And what's important is what you have to marginalize over here. And so the key things to marginalize over is the galaxy bias, of which you don't know the exact amplitude, since this is complicated galaxy physics. And then this parameter, this BV, this comes from the fact that our overall velocity normalization is also not correctly known, because we are not perfectly known, because we don't know the overall, the overall number of electrons. We don't know the normalization of the electron profiles in the galaxies, basically. So we try to take into account all relevant statistical effects. And then you can calculate, find an approximation for the Fisher matrix. And only recently, Marcel and Urs Seljac have done the same kind of method with lensing, and their analysis also applies to the KSC. In the end, I'll actually compare bit lensing and KSC. And you get something that depends very strongly on this correlation coefficient, which is the correlation between the galaxies and the velocities. And if this is a good correlation coefficient, a high correlation coefficient, then sample variance cancellation will be effective. And this is the case here. Okay, so let me see. Okay, so so this is a forecast example here. So what these numbers tell you here is that for specific baseline combinations of experiments that we have chosen, this here being close to LSST, this here being close to DESI, you get a certain improvement factors here. However, these here you should not yet. I'll have a forecast that is more complete, so you don't take too much value on these numbers. What I want to point out here mostly is that what counts is that you have a high galaxy density. And the reason for that is that for sample variance cancellation, you need to measure both modes well. You need to measure well the unbiased mode and the biased mode, of course, which is why for galaxies alone, this is a well-known thing. This is the sample variance plateau here. If you had only galaxies in your survey and not this sample variance cancellation, then more galaxies would not help you any further, because at some point you measure the modes well enough to measure kind of the power spectra, but your cosmic variance limited. Well, when you have the sample variance cancellation, in principle, with increasing galaxy densities, your error goes down and down and down and down, and this is what here happens in the KSC case. All right. So before I come to like a more complete forecast, maybe two more things. So one thing is, where does the signal actually come from? And here you can kind of you can cut your Fisher matrix at different momenta, different like spatial scales. So you see that it's a large scale effect, as you would expect from this chi-square dependence. You see when it kicks in roughly. It tells you also that a large survey volume will be important. And the other thing is here this correlation coefficient that we have illustrated here for a more DESI-light experiment, and here for one that is like LSST. And you see that, so LSST has photo-Z errors, which kills like small-scale information. But on large scales, the high number densities really help you, and here you get correlation coefficients in excess of 99%. Okay, so there are various smaller corrections that might be relevant here that we are also considering now. But okay, so now let's go to a forecast. So this uses now CMB-S4 and LSST. We have somewhat binned our forecast in 5 redshift bins for like technical reasons, because the bias depends on that. And now this is for galaxies plus KSC from CMB-S4, and this is for LSST only. And if you do that, you find that with our method here, you get about a factor of 3 improvement for all these redshift bins up to redshift 3. And this uses the LSST like gold sample number densities, which are plotted here. So with this method, it seems that you can go like near this multi-field inflation target that's sometimes given from theorists to experimentalists. You have to go below FNL equals 1. So of course a soft bound, I guess. But yeah, so this would lead you to, this would give you a 2 sigma roughly on this effect. Now there's one, so this looks very nice in principle. So there's one thing one should make as a disclaimer when giving this 3 and this improvement factor of 3 is that the original idea of sample variance cancellation was to split your galaxies into different biased bins, and then you get some sample variance cancellation between these within your galaxy sample, because you get, let's say you measure a sample with a bias of 2 and one with a bias of 1.5 or something, so this also gives you some sample variance cancellation. But it's not very well known how well this can be done in practice, while our KSC method is for sure gives you a bias of 1 sample. There's no, so because it measures all the matter. Yet, so if you assume that you could do this internal sample variance cancellation of galaxy perfectly, in the sense that you can split mass spin them and you know the relation of the mass to the bias, then you get this kind of forecast here. And this shows you that here, then you go down to an improvement factor that is at most a factor of 2 or so. And at some point here, even there is no improvement anymore at this point. And this is set to scale by the fact that here the halo bias actually becomes exactly 1. And then your galaxies also give you a sample at bias of 1. And they have the number densities here is much higher than here. So this reference mode kind of dominates the overall noise. So that's more, it's more comment for the experts on this method, I guess. So, but it means that in this case, like our method is less of an improvement, but it still gives you some gain over, except for specific parameters. Okay. Yeah, and something now that I did recently. Now, as I said before, Ulrich and Marcel have published the same kind of idea with CMB lensing last year, and so the idea there is the same. The CMB lensing measures as a probe of the matter of the total matter distribution, so the unbiased matter distribution on large scales. And so you could cross-correlate that with the CMB, and this would also give you some measure of FNLs for sample variance cancellation. And we are currently trying to make like a joint forecast of these 2 methods. This is with a student of mine. And so this is somewhat preliminary. So this here shows the galaxy convergence. So convergence is the CMB lensing, basically the lensing potential. So this shows that this convergence cross-correlation factor here can be like something like 0.5 or 0.7. This reproduces exactly what Marcel had in his paper, so we use that as a cross-check. And then we also put this KSC tomography in spherical coordinates that I showed you before. I used this flat sky box kind of approximation, which is of course not the true observational geometry. And if you want to do this, so first we transform this KSC tomography to multipoles, and then you have to do these Bessel integrals. And because you need such high resolution in redshift and in L, these are pretty hard to do. And you see some things, for example, that CLVG is at the redshift, like on the diagonal, is actually pretty much uncorrelated. That's because the matter, like the radial velocity is given by the matter, like in the neighboring shells, basically. Okay, so anyway, so we did this, and now I'm showing you here one plot that combines lensing and KSC. But I want to say that it's a preliminary plot. It does not include, for example, photo-C errors. And it uses a full sky observation, which is not realistic, so you don't get full sky CMB and full sky galaxies. But anyway, with these approximations, and then the galaxy density up to redshift 7, which is for LSST, which is also kind of an optimistic thing, we find that that for like very little redshift bins, that means very poor redshift information, basically. Lensing does give you a big improvement over galaxies only. But when you use more redshift bins, and in principle you should have the redshift resolution to go in this range here or so, then it turns out that in total galaxies plus KSC, so the galaxies are the dominant signal. So then lensing does not really seem to contribute much anymore if you can, with these parameters. And the reason why lensing would contribute something extra is that lensing probes transverse modes, while KSC probes radial modes, but lensing has less, like the correlation coefficient is not as good. So in summary, what I want to say, it seems that KSC is for this application for FNL is better suited than lensing, and seems to be quite promising. Okay, one word to systematic effects. We have we have calculated these so our reconstruction noise. There's some halo model calculations here. So PGE, and you need PGG, like the cross power of galaxies and electrons. We calculated these consistently in a halo model approach. We took into account this optical depth degeneracy, and we included photo-Cs and RSD errors, but not catastrophic photo-C errors. This is something for observers that's also important. Okay, to conclude, it's an interesting probe for FNL. We get an improvement factor of 2, a factor of 3 or so with our method, without additional investment in data, right? So this uses just the experiments that are upcoming in any case. We also tried with lensing, and for some configuration it does help some, but overall it seems that the KSC would give the dominant signal for that. Okay, thank you very much.